Hello. I'd like to welcome you all to this evening's lecture. My name is Brian White, and I'm chair of the Stanford Mathematics Department. This lecture is one of a series of public lectures organized by Stanford's Mathematics Research Center and by the Friends of Stanford Mathematics. This evening, we are very fortunate to have as our speaker Professor Tadashi Tokieda. Professor Tokieda is a leading expert in applied mathematics, particularly the mathematics and physics of fluids. Professor Tokieda has a very unusual background. He started out in classical Japanese painting and has had his work exhibited in a gallery in Tokyo. Next, he trained as a linguist, first in France and then at Jochi University in Tokyo, where he completed bachelor's and master's degrees in classical philology. Although today's lecture will be in English, Professor Tokieda could just as well present it in Japanese, French, Spanish, Russian, Greek, Latin, or Finnish. Fortunately for us, Professor Tokieda went on to develop an interest in mathematics. He did a second undergraduate degree, this time in mathematics, at Oxford, and then went on to get his PhD in mathematics at Princeton in 1996. Currently, he is Director of Mathematical Studies at Cambridge University. In addition to his mathematical research, Professor Tokieda is very involved in mathematical outreach. In particular, he is famous for his toys, which have been featured in the Royal Society's Summer Science Exhibition 2007 in London and at the Sorbonne Academy in Paris for the Henri Poincaré Centennial. He also regularly teaches at the African Institute of Mathematics in Cape Town, South Africa. Please join me in welcoming Professor Tokieda.
Every day around the globe, billions of people drink from cups. One day, one of us started tapping on the cup. We have the same sound, the same pitch from all over the place, all 4 points. But then it occurred to me to tap a little differently, somewhere else. Oops, no, sorry, this one. Those 4 points emit a single pitch. Those 4 points are common pitch, but a higher pitch than before. What is indeed going on? Thank you very much for pointing that out. It has to do with the handle. But if it has to do with the handle, wouldn't you have thought that this half of the cup closer to the handle and this half farther from the handle should behave differently? But that's not how the symmetry is broken. The point nearest the handle and the farthest from the handle behave exactly the same way, whereas 45 degrees off, you get a higher pitch. This asks for an investigation. Let's forget about the handle first and see why all those 4 points each time emitted the same pitch. That's because, you see, let's forget about handle. When I tap here, I'm making this point vibrate. And in response, the point opposite, diametrically opposite, can respond in one of the two ways. As this is vibrating like that, the other can do it like this, or go like this. But the first one, this one, is effectively moving the cup back and forth as a whole, as a rigid body, which doesn't deform the cup, doesn't change the shape, which is not involved in the production of the sound. Therefore, the one that's involved in making the sound is this one. But you see, a cup, if it can help it, wants to keep the same volume at all times. So in order not to be over-squeezed, when these two go in response, these two go out, and when these two go out, these two are sucked in. That's why you have this losange or square shape, boom, 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 boom. Any of the 4 points that you hit will excite the remaining 3, and the quadruplet of points that form the corners of a square always work in unison. They sing together. That is why you get the same pitch if you hit those 4 points or if you excite any of those 4 points. But why those 4 points, 45 degrees off, are higher pitch than those 4 points, lower pitch? In order to do that, understand that, we have to resurrect the handle that we have been neglecting. You see, what happens is that when those 4 points are being excited, that vibration as a whole must drag the handle with them. You see, because the handle is attached to one of those points vibrating. Whereas those 4 points, you remember what happened? I'll turn it around like this. When this goes in, this goes out, this goes in, this goes out. You see, in between, the point to which the handle is attached to a good approximation is not moving. That's called a node. So as far as those 4 points 45 degrees off are concerned, it's as if the handle were not there. So now you have 2 elastic systems. You can think of them as springs. One of them is attached, I'm talking about this one, to a heavy handle, heavy mass. The other one, not attached to any mass. And when you let them go, what you hear, the heavy spring will go whoom, 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 very sluggishly. And light one goes hee-haw, hee-haw. And that's the difference of the pitch that you hear. And so we understand all of this. So far, we have been understanding the following problem. We knew where the handle was, and we tried to figure out what kind of sound pattern we got. But the inverse problem is also quite interesting. Since we're talking about pitch, let's suppose that we are in a pitch dark room. We can't see anything. For example, I take off my glasses. So we don't know where the handle is. Indeed, we don't know what the mass distribution of our object is. But suppose that we are allowed to go around the cup. You don't know what the cup is because I'm not showing the cup. But go around, tapping everywhere and to record the sound pattern. From that recorded data, can we reconstruct where the handle is? You see, instead of knowing the conditions of the problem and then solving the problem forward and predicting the effect, rather we are talking about knowing the observed data and reverse engineer that in order to discover something about the cause that's responsible for the observed data. That's the inverse problem. And if you think about it, much of scientific activity is indeed about solving one inverse problem or another, so it is a very, very important thing. And this example, very simple example of cups, shows that the inverse problem may not be solvable. Indeed, we understand that whether the handle is at east, north, west, or south of the cup, you agree, the same kind of pattern of sound as far as those 4 points are concerned. Because those 4 points of the corners of the square always work in unison. Even worse, instead of having a single handle, you could have 2 smaller opposite handles, or 4. You can't even tell the number of handles. So the inverse problem is not solvable. However, up to symmetry, you can start saying something that is the beginning of a new adventure, it turns out, in science. We have been thinking about the behavior of a single toy. But now let's think about a toy that involves multiple particles, multiple bodies. Here is a soup bowl that I borrowed from a canteen in Cambridge. And a box of tea. The cover says Chai Gruzinski Extra, which I bought in a street market in Bordeaux. And inside there is a cover, probably it's not easy to see, как заваривать чай. Very scientific and detailed explanation about how to brew a good cup of tea and so on. That has nothing to do with our experiment. I'm just carrying around my cedar balls inside. And now, one thing that you can say about this experiment is that it smells nice. You can't say that about many other experiments. And if I put, say, 2 or 3 cedar balls and swirl, I do this, where you see that the cedar balls circulate in the same direction that I'm swirling. No surprise there. But now, let's increase the number of cedar balls. I made them more crowded. Then, if I swirl, they start going in the opposite direction. I'm swirling this way. They circulate in the opposite direction, so there was a transition. With one, it goes around this correct way, 2 correct ways, 3 correct ways we saw, 4 still fine, but 5 there is in fact a lot of hesitation. At 6 and 7 there is already a definitive tendency to start going the wrong way. It is a little like, I would like to say metaphorically, a phase transition. That is, when gas condenses to liquid or liquid freezes to solid, or the other way around, solid melts into liquid and liquid evaporates to gas, it's a little like this. And the point is that those balls, when there are not so many of them, are independent particles. They don't talk to one another, they don't touch each other. So they're just being driven by the wall, bumping into them, and they're sent in the direction of that the wall is sending them. So it's a momentum-driven motion. Whereas, when you increase the crowdedness, that is the order parameter, those balls are in contact among the neighbors. And what is lost is that when there is a momentum that's input from the wall, well, that's scattered among the neighbors. They don't go anywhere. However, instead what is not wasted is when the wall rubs against the ball is set in rotational motion like this, because you're rubbing, and that rotation is transmitted to the neighbor and so on, and they all start rotating together. That is an angular momentum-dominated regime. So there was a transition from gas to liquid. Indeed, gas, independent free particles. Liquid, the molecules are all in contact with one another. They can slide past each other. There's some freedom, but they're very tightly bound together. So it is a bit like this, to convince you that it is really like a phase transition. If you keep increasing the order parameter, then it freezes solid also. Okay, that's it. When we talk about phase transitions, we always think about some system with an extremely large number of degrees of freedom, but this is probably the world record for the smallest number of degrees of freedom for at phase transition sorts. Now, as a comic relief, I'd like to show you something really silly. We saw the balls circulating in the wrong direction. It changed the direction of rotation. It changed the chirality or handedness. Here I brought a nut and bolt. The nut is fairly loose, so it can spin one either way, and a cheap toothbrush that I happen to have bought in Princeton, New Jersey. And it gets going when I switch on the switch. Now, if I press the vibration against the bolt, well, it will just shake the bolt. But there's no reason why the nut should start to spin one way or the other. It just shakes. Shake is completely symmetric, and it does not have any chirality, that is left or right-handedness. It doesn't spin this way or this way. However, I haven't done this for a while, in fact, and it works only in front of friendly audience. If I channel my oriental energy into this, notice that it's going up against gravity as well. I knew that there were some suspicious people in the audience. This is really a special performance. In order to do that, I have to, you think that I changed the nut and bolt, did you? So let's see, but I really have to concentrate now. I think I deserve some applause for this thing. By the way, the cedar ball experiment is a variation on a phenomenon originally discovered by Igor Rehberg. The next toy that I would like to show you, set of toys, is a gift from Andy Ruina of Cornell University. Those two, can you see, those two heptagons, or regular 7-gons, are made from the same material, I can guarantee. They have the same surface coating. They have the same weight. Also, finally, and a little subtly, the mass distribution within each is uniform. In other words, I'm not hiding anything. It's not that there's some cavity hidden inside or there's more mass concentrated along the spokes. None of that. What you see distributed in volume, so to speak, is exactly how the mass is distributed. Okay, there's nothing hidden. Nothing hidden in them at all. And yet, when I try to roll them, one of them, rolls quite happily, whereas the other one refuses to roll. And if I try to roll them together, a dramatic difference in the dynamic behavior. And yet they look the same. If you superpose them and look through, you don't see the difference. What is different about them? And we might come up with some possible explanations for the difference, but then you have to convince yourself that that's surely a very, very tiny difference because you can't possibly see the difference here, even if you come up close. Well, so such a small error, tiny difference, is capable of causing a big and qualitative difference in the dynamical behavior. You should be able to convince yourself. That's usually not the case, right? If you have a ball rolling happily along, and if you put a tiny, tiny speck of dust, well, it just keeps rolling as before. How come one of them refuses to roll, whereas the other one rolls happily, whereas there seems to be no difference? It turns out that those are not regular heptagon 7-gons. One of them isn't. The one which rolls is a regular heptagon, but whose sides have been slightly, ever so slightly bulged outward to make it slightly round, curved a little bit. Whereas the one that refuses to roll is a regular heptagon with straight edges. How does that make a difference? If you round the edge ever so slightly, let's say by a tiny, tiny amount, which mathematicians like to call epsilon, well, then when the polygon wants to roll, you see the point of contact starts from one corner of the heptagon and then can continuously transit over to the next corner. You are doing something like this. Okay. So that's nice for the polygon. It can roll. In contrast, when epsilon becomes 0, there's a problem. It's really strange. You see, that rolling and continuous transition is possible however small epsilon is. When epsilon is 0.1, that's fine. I can just transit continuously. When epsilon is 0.01, it's still fine. 0.000000001, it still rolls. In fact, for every epsilon, provided it's not 0, if it's ever so slightly positive, you have the prediction of the theory and the experimental evidence that it rolls. So you always have the same prediction, bum, bup, 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 whatever epsilon is. It's therefore tempting to think that when you take the limit of epsilon being taken to all the way to exactly 0, the prediction will be the same again. But no, because in that case, you see, as the polygon wants to roll, the point of contact is stuck at one corner because the entire edge is now straight. And as the polygon starts falling, the point of contact cannot move. It's stuck in a corner. And the entire edge is in levitation. It's in thin air. And keeps going down, 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 until the next point, the next corner goes bang against the table and dissipates the entire energy and kills the motion. We have now an example of what in mathematics and mathematical applications is called singular perturbation. You have a model that depends on epsilon. This is a roundedness in this case. And you have some prediction of the model when epsilon is not 0. When epsilon is 0, 0.1, 0.001, 0.000001, it's always the same prediction, roughly speaking. But when epsilon becomes 0, the prediction is completely different and the behavior breaks itself. Very challenging and very interesting situation. And in this particular case, the roundedness of epsilon, so how much I bulged out, or rather Andy bulged out, is of the order of 0.1 millimeter. If you notice that the diameter of the heptagon is about 10 centimeters, that's less than 1 in 1,000. or so, a minuscule error of 1 in 1,000 is responsible for this dramatic difference. The most famous example of singular perturbation in mathematics probably is Navier-Stokes equation, which describes the motion of viscous fluid, but that's an infinite dimensional system. And here, again, a world record, I think, for the smallest and simplest number of degrees of freedom, and yet a singular perturbation. We've been handling heptagons. Another digression. You know, perhaps you took geometry in school, or you vaguely remember that kind of thing. And, sorry, I'm going to have to change the, and you might have learned how to construct an equilateral triangle, or a square, or a pentagon, and so on, with ruler and compass. These constructions are usually quite difficult, and there are theories about them. I'd like to share with you today a very, very easy way of constructing a regular pentagon that is a 5-gon. And you don't have to know anything. As with most of my toys, you don't have to be intelligent because nature is intelligent. You take a strip of paper, and then you tie a knot, the simplest knot that you can imagine, like this and like this, okay? And then I tighten the knot, at the same time flattening it. I tighten and flatten, tighten and flatten, tighten and flatten. And then I keep tightening it and flattening it, tightening and flattening it. And when I finish, I have a tight knot which is flat like this. And in order to show you what we have obtained, let's take away the part that's sticking out and show you what's in the middle. What's in the middle is a regular pentagon. If you go to Japan and stay in a traditional inn, they lend you not only a pyjama, but a belt, a cloth belt. And usually we fold the belt in a pentagonal pattern like this, so it is an ancient art. And by the same token, it turns out that you can construct any regular polygon, regular n-gon for all n. Now, many people in the audience are mathematical colleagues of mine, and they're going to come and lynch me because you're not supposed to be able to construct such things. But that's with ruler and compass. You see, when I made the pentagon, I made one pass, the simplest knot. Just one pass and knotted it. One pass gives rise to a regular pentagon, and it turns out that 2 passes will give you a regular heptagon, 7-gon. 3 passes, 9-gon. 4 passes, 11-gon. You get the idea. You might ask, well, what about even number of sides? Well, once you have a regular odd-gon, it's easy to divide, bisect each angle, so you can get access to all the even-gons as well. But anyway, this way, you can construct all the regular polygons. You might wonder, well, is that true? Well, it is, because on a long flight, I folded a regular 11-gon, which, by the way, if you learn something called Galois theory in university, in mathematics departments such as Stanford, you learn that it is not possible to construct such a thing with ruler and compass. Are you suspicious? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 gon, regular 11 gon. And all you have to do is to make a number of passes and tighten and flatten. That's all there is. Another objection is, well, okay, but after one pass, you already get to 5. How do you get the regular 3-gon, that is an equilateral triangle? In order to do that, you have to have 0 pass. And here is the picture of the 0 pass. If you just fold back and wiggle a little bit, in the middle, in the back of that picture, there is a regular 3-gon that is an equilateral triangle. Let's come back to our experiments. Every once in a while, you run into people who happen to be carrying around an inclined plane. And I brought here a jar full of beautiful basmati rice from India. And here is a jar full of beautiful air from California. This is full, let's call it 1. This is empty, let's call it 0. I propose to let them roll down the slope. It goes down quite fast. The other one also goes down quite fast. Well, not exactly the same way sophisticated people say because the moment of inertia is doing something, but roughly the same way and quite fast. So let's say they go down more or less at the same rate. What we would like to investigate now is how does the rate of descent change depend on the amount of stuff inside. This was full, 1, this was 0. So you can think of plotting a graph of how fast you go down as a function of against the amount of stuff inside, between 0 and 100%, if you like. In order to investigate this, let's take the case when the jar is 2/3 full, or, depending on your optimism, 1/3 empty. Now, there are 3 possibilities on there. How fast does it go down? Well, it might go down faster than 0-1 case, or it might go down slower. Or if you believe in that story of Galileo dropping 2 unequal masses from the Tower of Pisa and they landed at the same time, maybe the descent rate does not depend on the amount of stuff, amount of filling, so maybe it will go down at the same rate as 1 or 0. So let's vote. Who thinks the 2/3 will go down faster than 0 and 1? Who thinks it will go down faster? Very shy? Who thinks it will go down slower? That's the option that most people, reasonable people, go for. Congratulations. And who thinks it will go down at the same rate as 0 and 1? Okay, good. And who's too shy to vote? Let's try this. Are you ready? It goes down very slowly. And not only does it go down very slowly, there is something interesting going on inside. It's probably a little difficult to see on the picture, but there is a continual landslide avalanche on the free surface, on the top surface, whereas in the rest of the jar, the grains are stuck to the wall of the cylinder. So they're stuck and turn around, and when they emerge on the top surface, the avalanche makes some noise and dissipate a lot of energy. That's how it rolls down. So it goes down slowly. We shall come back to that, but in the meantime, let's try the 1/3 case, which is complementary, so to speak. It's paired with 2/3. Now there are 4 possibilities. Maybe it will go down faster than it's the champion, faster than everyone else. Or maybe it will be the slowest. Or maybe it will be faster than the 2/3, but slower than 0 and 1. Or, if you have a beautifully symmetric mind, you might think, well, maybe there's something symmetric between 2/3 and 1/3, or f and 1 minus f, if you see what I mean. So maybe it will go down at the same rate as 2/3. So, who thinks the 1/3 will go down faster than everyone? That's the intrepid solution, and I congratulate you on your courage. Who thinks it will be the slowest? Yeah, slowest. Who thinks it will be faster than 2/3, but slower than 1 and 0? That's the majority, and that's the option that most reasonable people go for. And who thinks it will go down at the same rate as more or less 2/3, apart from error? So, good. Let's try this then. Nothing up here, nothing up here. Are you ready? I release. What? It stops completely dead. It's so reluctant, it stops so completely that even if I cajole it to roll down, it doesn't want to. Completely dead. Why was the 2/3 one slowed down and 1/3 one immobilized? The secret came to my mind after discovering this phenomenon, and has to do with a very interesting characteristic of grains, be they rice, as in this case, or sand, or flour, or whatever. When you were a child, or when you take a child and go to a beach and try to make a sand pile, sand mountain, you try to make it very, very steep. By the way, it should be dry sand, because with wet sand you can sculpt all sorts of things, but dry sand. And we want to make it really steep. Well, you can make it only so steep. If you try to make it steeper than that, it starts to collapse and avalanche and settles at some inclination. That limit angle to which you can make something steep, a grain steep, is called angle of repose, which I denoted by the Greek letter alpha in green. And you cannot make it steeper than that, and that's the limit angle. By the way, if there are granular flow experts in the audience, I know that there is an angle at which the avalanche starts and an angle at which the avalanche stops. These are slightly different, but for our purposes, that's not important, so let's talk about a single angle. So that's alpha. Please note that that's for grains. If you're talking about, for example, water or milk or honey and so on, then you cannot sustain any angle. If you make a pile of honey, for example, well, initially you might have a bulge, but if you wait for long enough, it's going to flatten out. So the angle of repose for liquid, however gooey, is 0. By the way, with this kind of experiment, you can actually try the same thing with honey, for example, or something even syrupier. Then it's quite interesting because you first put it, and then it doesn't seem to be moving. You still watch, it doesn't move. You watch, it doesn't move, and you get bored and go and have coffee, and when you come back, it's moved a little bit. And what seems to happen is that, contrary to the initial, perhaps, guess that, well, it's going to creep very, very, very slowly, on the contrary, it sort of goes in jerks, very, very, very intermittent jerks, and it comes down. Anyway, you can make a watch out of this or clock out of this, and that would be an interesting project as well. So, angle of repose. Now, let's look at the case when the jar is almost full, let's say. In that case, you agree that the center of gravity of the grains, or the jar plus grains, is more or less in the middle of that circle that represented by the cross-section of the jar. So gravity is pulling down at the center, roughly speaking. On the other hand, the point of contact between the jar and the slope is indicated by that red dot. And you see that the point of contact is on the uphill side of the arrow of gravity. What does that mean? That means that when the gravity pulls down, its torque, or the rotational effect, is to roll the cylinder downhill in the clockwise rotation. In contrast, imagine that there aren't so many grains. The jar is almost empty. Then you can create a situation where the gravitational pull at the center of gravity is to the uphill side of the point of contact. That is, the red point of contact is on the downhill side of the green arrow. Then what does the torque of the gravitational effect do? Well, it's curious. Although the gravity is pulling down, it tends nonetheless to rotate the whole thing counterclockwise. That fights against the descent. In fact, it rolls the whole thing up. And you can actually see this effect. When I release this very gently, and it's going to be subtle, so please watch. You see, it went up a little bit, yeah? And then it tries to find its equilibrium. That's why it rolls uphill, or it doesn't want to go downhill. You readily check by doing simple geometry that this can happen only if the angle of repose alpha, that's green, is strictly greater than the angle of inclination of the support, which is beta. Otherwise, it doesn't work. For example, in the case of fluid or liquid, alpha is always 0, so this effect cannot happen because 0 cannot be greater than a finite angle. Okay. So, if we now try to systematize our experimental data and plot the cartoon graph of our experiment, here's what it looks like. So the descent rate is vertical, and how full is horizontal. You see, at 0% and 100%, you have a fairly fast descent, so the points are way up there. But somewhere in the middle, there's a whole basin of immobility. It doesn't move at all when that angle repose effect kicks in. What's furthermore interesting is that, okay, if you step a little to the right-hand side of the basin of immobility, that is, if you come closer to 100%, it rolls. That was the 2/3 case. And when it rolled, you recognize this familiar case. There is some sort of continual avalanche on the free surface that's sort of dissipating energy and so on. And these grains are effectively acting a bit like what we call viscous fluid, that is real fluid with viscosity, stickiness, internal friction, and so on. That's exactly what viscous fluid does. Now, let's then try to step the other way. From the basin of immobility, what happens if we try a jar which is closer to 0%? Yeah? Here is one. It contains very, very few grains. And now it's near 0. How shall it behave? It goes down. But the way it goes down is quite remarkable. Again, perhaps the details are not so easy to see, but it has a sort of jerky motion. And the whole body of, if you like, the whole collection of grains are stuck as one, and they are sliding back and forth inside together. There is no avalanche. There is no free surface phenomenon. So on this side of the graph, it turns out that you have this peculiar motion. It descends, certainly, but all the grains are sort of dancing together, back and forth, sliding on the surface, and there is no avalanche. In fluid mechanics, the area of engineering and science that's called fluid mechanics, this is a typical phenomenon associated with inviscid fluid, that is, fluid with zero viscosity. It slips on the boundary, and that's how it behaves. Now, people who have been studying fluid mechanics, and some of the greatest applied mathematicians from the 19th century onward, know that the theory, mathematical theory for inviscid fluids and mathematical theory for viscous fluids are not very compatible. In fact, there are really, really big differences. Here is a phenomenon, nonetheless, perhaps one of the few ones, where in a natural, very simple tabletop experiment, very cheap also, you just have to buy some nice grains of rice, two incompatible mathematical theories are inhabiting the same phenomenon, on the one side, on the other, separated by a rather flimsy basin of immobility. So experimental challenge and theoretical way forward, I'm doing this work with Nicolas Taberlet in Lyon, is somehow to play with this so as to reduce that basin of immobility narrower and narrower and narrower, and make those two regimes that are theoretically incompatible touch each other. And then Mother Nature will have some really tough decisions to make. Okay. That was the viscous inviscid conundrum. And it had some fluid resemblance. So let's actually do real fluids. Here is a traditional Japanese toy called kamifusen, literally meaning paper balloon. It's made of very wrinkly paper and very thin, and there is a hole there. So the way to blow it up, of course, is to put your air through the hole, and then it becomes round. And notice that once it's round, it's quite bouncy. Okay? It's quite bouncy. It has effective elasticity. That's quite nice. But there's another way to make it round. I crumple it completely, and then start hitting it, tossing it. Now, when you hit on something, don't you have the impression that you should be denting it and therefore making it less round? And surely when you hit it, you make it less and less convex. I mean, right? You're hitting it, you're denting it. But look what's happening. I'm just hitting it randomly. And the result, all that denting made it round. This is a way of making something rounder by denting it. That's really strange. What is happening in this traditional Japanese toy, kamifusen? There are some experiments going on right now, actually, at Harvard, which try to do this experiment in vacuum, for example, and also when we hit it hard and so forth. Now, I think what's happening, and this is still work in progress, so I'm sharing with you some really sort of dirty laundry, so to speak, is this. Sorry, let's go back a little bit. The key is this. When I crumple it and release, let go, it doesn't actually stay completely crumpled. Watch what happens. It starts recovering its shape a little. It starts fighting back, but not all the way. So it's not elastic like a rubber, but it has some memory of what it used to be. Yeah? So I think what's happening is this. Imagine that you have this balloon, fairly crumpled, but not too much on both sides, left side and right side. And I hit it on the left side. Upon hitting it, I make the left side, the side that I hit, super wrinkled, over wrinkled. The other side, by recoil, or the gush of air, poof, gets puffed out and becomes slightly rounder. But the over wrinkled left-hand side starts recovering its shape a little bit. It starts relaxing. And so per each cycle, I'm about to hit it again, you see I increase the overall smoothness or roundedness because the side that I hit got super wrinkled but de-wrinkled, unwrinkled, so it's more or less the same as before, but the other side got puffed out and stays smooth. So if I keep hitting it on all sides, what you see is this behavior of the volume against time. Each time I hit, I instantaneously, boom, decrease the volume, shrink it. But then there's a slow recovery, but not too slow as to recover before the next hit. So hit and recover, hit, recover, and then you gradually approach the spherical shape. Nature, it turns out, is full of phenomena where lots and lots of different scales live together. The most famous example, perhaps, is turbulence in fluid mechanics. That is a huge mess of flow that is going all over the place. It's really not nice. And it turns out that turbulence contains many, many large-scale vortices, medium-scale vortices, and small-scale vortices, and so forth. You know, it keeps going down. And what happens, it turns out, is that large-scale vortices pass on some of the energy to the medium-scale vortices. Medium-scale vortices, in their turn, pass on some of the energy to small-scale vortices. There is what we call the cascade, or passing of energy from large to small. Large to small, always going downwards, and that is a typical case. Whenever you have a multi-scale problem, that is a phenomenon with lots and lots of different scales, so they're interacting and talking with one another. Those experts of fluid mechanics in the audience might say, but in two-dimensional turbulence, the cascade is not like that, but that's a mathematical model, so let's put it aside. But you see, this Kamifusen is very interesting because, as you can see, in the beginning, there are lots and lots of very small creases, so very small square things. But as they expand, those small creases give way to those large creases. For example, they are sort of valley-like, dents and so on. That's what I mean by a large crease. And at the end, they all disappear, and creases become basically infinitely large as far as the scale of this thing is concerned. So the energy or the information is passed from small scale to large scale. That is, what we have is an inverse cascade. It's going up. And as far as I know, this is one of the very few truly natural and simple physical phenomena where the cascade is inverse. It's going upward. So far, we have been playing with lots of different models. And sometimes there were singularities, sometimes there were perturbations and so on. Sometimes there were strange things going up rather than going down and so on. But we now would like to be more ambitious, and we'd like to see those singularities, things that break, and where theory no longer works, in a single object. And now, Joe, can you lend me some coin? Thank you very much. When you drop a coin, you hear this very characteristic noise. So characteristic that if you hear that noise in a restaurant, you know somebody dropped the coin. Now, thank you very much. And this is an exaggerated coin. It's very, very heavy, and you can believe the kind of problem that I have going through airport securities with this. And because it's so heavy, when I launch it, we can see many interesting details that escape our attention otherwise. It's being driven by nothing. It's going on its own. It's a purely inertial motion. And you can see that something is going faster and faster. But note that the spin rate is not that great. It's like this. Nonetheless, something going faster and faster, getting accelerated. What is going faster and faster? It's not the spin. Faster and faster, faster and faster. I'm not doing anything. It's just going on its own. It's lasting longer than I thought, but eventually it will come to a halt, and when it does, I'd like to invite you to pay attention very closely to what you see and what you hear. You might have noticed that the mirror is slightly dented concave, but you don't need a mirror. I can do it on the table. It's a little noisy. So something seems to be diverging, going off to infinity, rising, 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 and goes through the roof. What is going through the roof? Well, there used to be a lot of controversy about this object, and there still is a little bit, I suppose. About 15 years ago, maybe 12 years ago, this excited a lot of people in applied mathematics. And some papers appeared that said, well, it has to do this strange effect of going up and up and up and going through the roof, this frequency divergence, has to do with the friction of the air trapped underneath the disk. Now, some people said, oh, but we did the experiment in a vacuum chamber and it behaves more or less the same way. But when you reduce the density of the air to try to make it vacuous, it turns out that viscosity, the frictional properties of the air, does not drop so readily. It was known to Maxwell, and then there was a lot of controversy. Now, at that time, I was in Montreal, a poor postdoc. I'm now a poor professor. And I had already figured out some simple model of this, but I wanted to do a vacuum chamber experiment. But you know how expensive a good vacuum chamber is? So I went instead and bought this from a ladies' accessory shop, a plastic bracelet. Now, I'm going to spin this, and there is no question of air trapped underneath the disk because there is no disk. It's just a hoop. And I'll spin it. I'll try to spin it in a nice way. A little nicer. Oops. Oh, sorry, I'll try to do it again. Here. It's like a ballerina who's standing upright and spinning, and it's very beautiful, but soon she'll become tired. That is the first regime or first type of motion, but when she starts getting tired, she'll transit to a new type of motion, new regime, and you'll see what happens. She's still fairly upright, spinning, but she's getting rather tired now. Now, please watch carefully. She's still upright, this ballerina, but she's about to transit. Now it's a new type of motion, and from that point onwards, you see it's exactly the same motion as for the disk. And there is no air trapped underneath the disk. Interesting. So the air resistance might play a role, but it's not the dominant effect. So what is going on? First, we have to understand that it turns out to be a clue. What happens to the energy? In the beginning, there's a lot of energy. It's going around very vigorously. At the end, all is quiet, so there's no energy left. Where did the energy go? Energy has to be dissipated. And it's not the friction of the air. As you see, the point of contact rotates and goes around. That point of contact is also the point of pressure. It's pressing against the support, table, whatever, and that makes the support vibrate. It's sending out effectively an earthquake wave, which goes away, carries off energy, and that is how the energy is dissipated, in my opinion. In order to check this, let's repeat the same experiment, but on a good absorber of elastic energy, such as a human body. You know, a human body, especially mine, has been designed to withstand all sorts of shocks. So when I do this experiment, supporting it on my hand, please watch how long the experiment lasts. That's it. The entire energy, elastic energy, escaped through my arm to the ground. I have effectively earthed the experiment. So that is where the energy goes. Let's understand then what is going on more closely. You noticed that something was going faster, but it wasn't a spin. It turns out that you can see this motion of the disk or the hoop or anything as a combination of a spin, which is going very slowly, but also a flapping motion, flap, 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 and that flapping is getting faster and faster. A good analogy that I'd like to suggest is a ball that bounces. Have you played with a super ball? When you drop it, it goes boom, 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 and so on. It bounces, ideally, infinite many times, but comes to a stop within finite time. And I'd like to suggest that that's a good analogy. So we'll pursue that analogy. The energy of this motion has to do with how high the disk is inclined. And you know, if you drop an object, in time squared, you drop a certain height, so height behaves like time squared. But frequency, how many bounces there are within a unit time, so hertz if you like, is 1 over time. So energy behaves like bounce frequency to the negative second power, to -2. On the other hand, let's think about dissipation. How is the energy lost? Well, this is really the core of the hypothesis. If you think that dissipation is due to friction and earthquake and so on, you can argue as follows. I denoted by T sing the time when the noise goes up, 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 and diverges. Okay, that's the singularity. And I'm measuring the time, not the time itself, but the remaining time to that singularity. And I call it T sing because that's when the disk sings. Okay, so that energy rate, loss rate, is, I'm going to assume, has to do with the flapping frequency. How, if it flaps faster, it loses energy faster. If it flaps slowly, it doesn't lose energy so slowly. That's a slightly controversial statement, but let's take it on trust and then move on. Well, in that case, I know how the energy loss is related to energy itself because, you know, I'm going to identify the bounce frequency with the flap frequency, and I know that frequency to -2 is energy. So I just write a differential equation, the kind of thing that you can learn to solve in an excellent department like Stanford Math Department. And the solution is very simple. It's energy to the power 3/2 turns out to be behaving like proportional to the time remaining to the singularity T sing. But also, we know how the energy is related to bounce frequency. Again, it's negative second power. So we reach the conclusion that the frequency behaves like the time remaining to the singularity to power negative 1/3, 1 over 3, negative 1 over 3. That's a very, very curious exponent. Here, we shall identify the frequency with the frequency of the sound that we're hearing. And Ariel Amir of Harvard recorded everything and plotted the result. What you see here is blue one is the recorded result with some noise, and red is the theoretical prediction. And look, by the way, the time is measured from right to left because I think Ariel comes from Israel, and in Hebrew you write from right to left. But anyway, look at this. It's smack through the experimental data. Nowadays, you can't get clean data like this. It's amazingly beautiful. And that's exactly the negative 1/3. That's the experimental data, and the theoretical prediction was negative 1/3. Okay. This negative 1/3 is quite interesting. And it happens here. It also happens in the following little experiment. These magnets are extremely strong. They're made of neodymium, one of the most magnetizable elements in the universe. And when I let them go, they do this. I can toss them. Did you hear that? Zzz, and that rising sound, that pitch, if you record it, analyze it, the data is not so clean as for this one, but it's still negative 1/3, turns out. It is time to bring this lecture to some sort of conclusion, and we have been seeing that through toys, we have gleaned quite a diversity of phenomena and scientific ideas. We have seen all those things on the left, that's those phenomena. On the right, you have the scientific ideas, and more. When we think of science, we have the mental picture that science is being done in institutionalized context, by professionals, laboratories, institutes, and on the pages of a scholarly journal. And of course, all of that is extremely important, and that's where we expect science to come from. That's where we expect science to be blossoming. But besides those sciences already in flower, I would like to suggest that we look for sciences in the bud. And that leads us to the main question of this lecture. Why toys? By way of an answer, I'd like to share with you an anecdote from a little-known work of Aristotle called De Partibus Animalium. In that work, he has an anecdote about Heraclitus, a pre-Socratic philosopher who flourished around 600 BC, and he was, so to speak, a science star of the time, a Stanford mathematics professor of the time. And young people come to see this person. And they expect, of course, Heraclitus, the great Heraclitus that we all heard about, to be, in magnificent robe and lecturing to a large classroom, or perhaps conducting a very, very complicated experiment with an expensive machine and so on. But what they find was different and surprised them. Here's Aristotle speaking, and my free translation. In all natural phenomena, there is something of the marvelous. There is a story that some visitors once wished to meet Heraclitus. And when they entered and saw him in the kitchen, warming himself at the stove and playing with the children, they hesitated. But Heraclitus said, "Come in, don't be afraid. There are gods even here. Enaigar kai entauta theus." There's another story, I can't help telling stories, about George Bernard Shaw, a great writer of Irish origin, and Winston Churchill. They were rivaling friends, and one day the story says, Shaw sent a letter to Churchill saying, "Dear Churchill, please find enclosed 2 tickets to the premiere of my new play in the East End. Come with a friend if you have one." And Churchill replied, "Dear Shaw, unfortunately, previous engagements prevent me from attending the first evening. I'll come to the second evening if there is one." I am immensely grateful, first and foremost, to all of you, my gentle audience, for being so generous with your company this evening, and to the Stanford Math Department, and especially to Brian Conrad and Brian White, and also to friends of Stanford Math Department, and some of my teachers, Yasha Eliashberg and Joe Keller, who gave me such wonderful hospitality on this heart-throbbingly beautiful campus of yours. One of the biggest joys of my small life is in exploring science with friends old and new like you. I hope there will be a second time. Thank you very much.
Thank you for a wonderful lecture. I think we have time for some questions, and there are microphones here. It might help if you can step out or else speak very loudly.
Howdy. Oh, wow. Thank you for the fantastic lecture. That was fascinating to see. I have a more quotidien question. I would really like to show this to my high school physics teacher. Is there any way I can access this online on the internet to share with him?
The question is there a resource available of this kind that people can use so that you can use them in teaching and with children and so forth? The short answer is not yet, but there is a project at MSRI, Mathematical Sciences Research Institute at Berkeley, to film my toys, and hopefully we'll archive them and make them accessible. So that's the short answer, but the long answer is the following. I think that have you had the experience of giving something some present very carefully chosen to a little child, very, very little child, and when you give the present, the child is completely uninterested in the present itself, but plays endlessly with the wrapping paper and the box. Yeah. And somehow that's the message. You see, we seem to be interested in things that are already labeled interesting, but the point of my message is that we should sort of look around ourselves and pick up daily objects or phenomena and extract interest from them ourselves. And in some sense, what I would very much encourage you to do, and I'd like to hear back from you, is to use objects of daily life and then explore. In fact, some of these things, of course, I brought a very well-made model, but many of them, for example, the coin that I borrowed from Joe Keller, you have in your pocket. This, ring cost me, I think, $3 Canadian. And, none of this really is an extraordinary object, but what you find in them, if you play with them imaginatively, is extraordinary, and they open up something. So I'd like to suggest that, of course, so the record of what is available and what kind of experiments we can do and so on, I would like to put them online, and there are also other resources. But as far as the experiments and also exploration and thinking about science is concerned, I'd like to encourage you to do it all on our own, in the kitchen, in the living room, in the backyard.
Hi. I was wondering if you could say a little bit more about the toothbrush and the... because I feel like I don't really actually understand what's happening.
The question from the gentleman is, can I say something about, really, can I spill the beans on the toothbrush and nut and bolt? Do you expect to get that information for free? Next question.
Okay.
Next question.
Regarding the coin, the round coin you're rotating, I have noticed there could be another phenomenon at work. The first coin, the point of contact, the circle of contact, is wider, and it goes and it goes narrower, narrower till it, of course, the limit is the coin. So there could be a conservation of angular momentum at play.
That's right. So the question is, maybe there are some other effects at play, at work, in this disk, or in general. And the gentleman's point, I think, is that depending on how much the angle of the inclination is with respect to the horizontal surface, the point of contact describes a large circle, small circle, and so forth. That means that the circulating point circulates around a very, very large circuit, a very small circuit. But there is something called angular momentum of conservation, and there's a torque, and you can calculate everything. So maybe that is going to come in. Now, your intuition, I think, is correct. But in the way we did mathematics, there is a way to sort of separate things very cleanly. And the angular momentum is fairly well conserved, it turns out, because there's no sort of torque coming from anywhere. But I've already separated that out. It's a mathematical device by saying, oh, the motion is going to be spin plus the flapping. So I'm saying that maybe I should show you what I mean. Instead of saying that it's a motion like this, can you see what I'm doing? I'm saying it's basically a composition of this, spinning, and this. Yeah? So first it's flapping this, and then flapping this way, and just flapping direction is circulating and so on. So I have isolated this accelerating part, which is the flap, into the other term. So indeed, I mean, something like what you're saying is certainly correct, but the way the analysis was done is to do this cleaner mathematical device and then not complicate the problem. Okay.
Hello. So thank you for the demonstrations, especially the ones with the rolling polygons and the one with the rice canister. To combine those two together, I was wondering, have you tried rolling a polygonal canister with rice in it? And if you did, how does it behave?
Well, I haven't, and that's called a young researcher. Exactly. You can come up with all sorts of problems, and some of them are interesting, some of them are not interesting, but we should come up with problems and we should investigate.
Thank you for the demonstration. I have a question about how many of these do you usually come up with a year?
The question is, how many of these do I come up with a year? Are you a funding agency or something? Well, you know, it depends on a good day and bad day. I mean, when I'm really depressed in a dark and damp winter of Cambridge, England, then maybe one every year or so when the sun comes back, which doesn't. When I'm in Palo Alto, Stanford, maybe one every second day or something. It depends. But I try my best to think about and sort of try to notice things around us. And you can come up with something every once in a while, maybe once a month.
I want to thank you again for the lecture like the others. I thought it was fascinating and inspiring for adults and children. I'm curious to ask a question. The initial experiment was with a cup, and you demonstrated how we could hear different tones by the way that it resonated off different points. A number of people will comment on the relationship between music and mathematics and the fluency of music contributing to mathematical aptitude. I'm curious if you had any thoughts or comments on that.
The question is there any relationship between mathematics and music? I'm completely incompetent to comment on this, so whatever I say is a personal sort of just off-the-cuff remark. First of all, I enormously enjoy music, but I can't play. Well, I used to play the flute, but what came out of it couldn't possibly be called music. So maybe not in all cases, but I think there might be something in common. You see, there is an interesting sociological phenomenon that both mathematics and music admit the existence of child prodigies. On the other hand, it's impossible to imagine a historian who is a child prodigy, right? I mean, you laugh, but in mathematics and music, why do child prodigies, why can they exist? And the answer is that these are very, very well circumscribed sets of extremely technical skills that you can, by concentrating, learn early on. So there is this technicality issue, and you have to overcome, and that's what you learn in school. You have to learn techniques, and the difference between people who have learned the techniques of this technicality and who haven't is quite sharp. At the same time, as in music, in mathematics also, there is the aesthetic sense, or making sense of everything, and that's quite so difficult to imagine in the case of mathematics, because in music, even if we cannot play the piano, we can still enjoy Rachmaninoff. But in mathematics, unless you can play, it's a bit like, you see, imagine that none of us has any hearing, but somehow or other, humanity discovered writing musical notation. Yeah? So there is no sound in the world, but some people started writing music. And after a while, after enough technical practice and enough civilization, many people might start enjoying reading music and composing music, although nobody can hear it. And that's a bit like the situation in mathematics. Yeah? You see, so if only we could hear, but we can't because of the nature of this. But you can actually enjoy reading and writing music and so forth. And in fact, there is a lot of meaning in the music. You know how deeply music can move us and in fact make us do things. So I think there is something common between those two subjects, but I don't know anything more than this. Interesting question.
So thanks for the awesome demonstration. So in a lot of the things you showed us, there seem to be certain limits in the properties where, like limits in the design of the thing where the properties would change dramatically. Mm-hmm. In your bio, it was mentioned you're like an applied mathematician. Have you found like graphs or functions that when like graph you can see graphs, and so what elements of those graphs represent these drastic changes in properties?
Good. The question is, in fact, all of the toys that I shared with you today, there is some sort of point where something breaks, something stops working, and there's a transition, there's a drastic qualitative change, singularity, and so on, discontinuity. And if you want to draw graphs of these things, yeah, as we learn in school, what features of the graph represent those interesting, rather dramatic, and rather dangerous points? And the answer is, for example, if you draw a graph freehand, maybe it's very smooth and you just draw it without lifting your hand off the paper, right? But you might boom, stop and cut it and then start somewhere else. That's called a discontinuity. So discontinuity is one signature of something like this. Another thing is maybe it's not smooth. It's less dramatic than this discontinuity, but nonetheless quite interesting. You might introduce a kink. It's not smooth, but you might suddenly turn a sharp corner. And that kind of thing, when you learn calculus, you learn that that's the discontinuity of the derivative, and that's also a signature, and so on. Sometimes there are even more interesting cases, weirder cases. You see, when you learn to draw a graph, it's sort of a hovering picture like this, but you might go back and so on. You see, the professionals will call it multi-valued, and that can be also an interesting feature. So there are some features, as you correctly guessed, of a graph which tell us that something really strange is going on, and that's where we want to focus our attention. Because the world is really, what we see in the world is made of shocks, made of singularities.
We have time for one more question. Is there a question?
So I too read your bio, and thank you for the amazing demonstrations. So I noticed how you've gone through many undergrad and graduate programs. Is there a reason why?
Again, I went to undergraduate school and graduate school. Why did I do this?
No, I mean like you went to like multiple stages.
Oh, multiple stages. Oh, that's easy because I started, when I first went to university, I was completely obsessed with languages. By the way, it's not true that I can give a lecture in Russian. That's not true. But other languages maybe. But so, I was really interested in languages, especially ancient languages, and I had no mathematical training. But later on, I thought, well, for a certain reason. There's a long story, and there are several versions of the story, by the way. But I decided maybe I'll try this strange thing called mathematics. I was not familiar with it at all. Well into my 20s, I had never heard of calculus. But I took time off, tried it, really liked it. And so decided to become a mathematician. But the quickest way, you see, to sort of try something was to go to school again. Yeah. Thank you very much.
Let's thank Professor Tokieda again for a wonderful lecture.